Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Inshallah, today we'll continue in the maybe first half of the lecture, continuing talking about formalization of the learning problem that we started last time. And then we'll start to talk about some limitations of machine learning. Okay? Before, inshallah, we study more machine learning models. Okay? Right. If you remember from last time, we viewed machine learning as a function approximation. Can you tell me what do we mean by that? Yes, Omar?
We have a set of possible input and a set of labels which are output. The true function maps every value to its correct one, and our job is to predict some function that is as close as possible to the true.
That is an approximation for that. Yeah, so we have set of input instances, right? Possible input instances. We have set of classes or labels, and there is a function that maps actually between the input to the output, or the input instances to the classes, but we don't know this function, right? If we know it, then we don't need to do anything, but we don't know it. So we have set of solutions or set of models, and we want to pick from this set one model or one function that will approximate the actual function, the actual true function that maps between the input and the output. Okay, so that's the view that we discussed last time. And then we said that to learn this function, we need to know two things. We need to know how good or bad our predictions are and how to model the data. We started with the first one, which is talking about how we can know that the predictions are good or bad, okay? And we model that by what we call a loss function. So the loss function takes the system prediction or the model prediction and the true prediction and compares between them, okay? And that was the simplest one. That will be 1 because it's an indication of error. It will be 1 if the two are not the same, and will be 0 if both are the same. And we also mentioned that the loss function depends on the type of learning, okay? And I think we discussed last time an example from regression, that this loss function will not be good for regression, but might be good for classification. So we need to think about this when we design our system, okay? Which loss function should we use? This is a big decision. That's a very important decision in our system. The second question was, where does the data come from? And we assumed here a probabilistic view that the data was generated by an underlying probability distribution. Okay, we called it D, and D is over both the input and the output. Okay, so every pair, X and Y, X is the input and Y is the output, every pair has a probability. Okay, so we assume that, and we don't know this probability, of course. But what we know from, what we know only is that we have some training examples. Okay, so we don't see this, we don't see all the possible pairs, but we see a very small subset of them, which we call the training data. And in order to evaluate our model, to know whether our model is really good or bad, we need to estimate what we call an expected loss. Okay, so the loss function, remember always that the loss function is defined on one example only. Okay, so the loss function will give me an indication of error for one example, if that example, the prediction for that example was good or bad. Okay, type. To get the expected loss over the entire data, over the entire possible data, we have to go through all the possible data. Okay, so that's what the formula is telling us here, that the expected loss is over the entire distribution of X and Y of the loss function, okay, which is the summation over the entire data set for every pair, for the entire possible data. For every pair, it is weighted by its probability. Okay, so if one pair, just to give you an idea here, if one pair of X and Y is very high probable, then it will be important that the system will give good prediction for that example, right? Because it is very highly probable. Okay? So that's why here the expected loss is like a weighted average. Every x and y pair has a probability, so we multiply that probability by the loss on that example. That's the expected loss, and we said that, I think that was the last point last time. Can we compute that? The answer is no. Why not? Yes, because we don't know these probabilities, right? We don't know these probabilities, so we don't have the distribution, so we cannot compute that. What we can compute is what we call the training error. Okay, or the loss on the training data, because that's the only thing that we have, right? We don't have the entire data set, we have only the training data. So we have just a sample of it, which is the training examples, x1, y1, x2, y2, and so on. Okay, so the training error on the training examples is the summation, is the average of the loss over all training examples. Okay, so this is the loss on the example number n small, and we multiplied, remember in the previous slide, we were multiplying by? No, that was the loss, the probability of that, right? Do we know the actual probability? No, we will assume that they are all equiprobable. The probability of every example is equal to any other example, because we don't know more than that. So that will be the training error. Okay, so the training error is the average error over all training examples. Okay, and when we say error, how can we measure it? We measure it by the loss function. We measure it by the loss function. Yes.
What is
N capital here is the number of training examples. Okay. Yes.
Training error problem is like when we have like the same training input and give us different.
No, we should not have. We should not have something like this. Of course, for every we have pairs. Okay, so for every example we have the label for it. We know the label for it. Okay, then we will test the model that we have on these examples. Okay, one by one, so that we can compute this.
Like we have a table. And
Yes.
In this table we have like two different rows. We have like we took in the examples. It's wizard. It gives us the same values in the input and in the output.
Okay, theoretically. Okay. Okay. So theoretically, this can happen. Okay, and practically also this can happen, by the way. Okay, because maybe you are not observing all the possible features, right? And you are observing some features. So the question here is that can it happen that we have two examples, same examples, but with different labels? Theoretically, yes, it can happen, but this will be kind of noise here in the data, right? So in this case, it will be counted twice, and for every one, there must be one will be an error in this case. Okay, of course, because the system will predict, unless there is some randomness in the system. Okay, but if the system is deterministic, then it will always, for this example, it will always give the same label. Okay. Any other questions? So this is how we can compute the training error. Yes.
So the loss function is given.
The loss function, what do you mean by given? We have to determine the loss function. The designer, okay, of the model, okay, should select the loss function. Okay. Any other questions? Right. This is how we can compute the training error. Is that sufficient for us? Yani now we can say, okay, now we can know the performance of the model because we can compute the training error. Do you think this would be sufficient? Okay, of course we need to minimize that error. Okay, but once I compute that error, the training error, خلاص, I know how the system will perform on average.
Yes.
Yes?
Yes.
Yes.
Depending on the sample.
Who is talking? Yes.
Depending on the sample size.
Depending on the sample. Okay, let's say that we have very large number of training examples. If we compute the training error, that will be sufficient? Type. The answer is no. Okay? And let's see why it's not the case. Okay? Remember that the goal is not to build a model that has 0% training error. This is not our goal. Okay? This is not our goal. And that would be easy. Why is that? Let me give you an example. If you think about the way that we built the decision tree, if we grow the decision tree until we have in each, until we stop based on the algorithm that we saw, what will happen? The decision tree learns everything in the data set, and for every training example, it will give you the right answer. Unless we have the case like what you mentioned, but this is a very rare case. Okay? So it will learn everything. It will kind of memorize the label for every possible training data. Will that be sufficient? Okay. Let me give you another example, maybe simpler example. I can have a table. You give me the training data, and I make a mapping table. If you give me that example, I will give you back the label for it. You give me the training data, right? I know, I see it, right? So I don't have to build anything. I just need to memorize that this example has this label, and I will return that label for it. What will be the training error in this case? 0. But did we learn anything? No. So it's very easy to get 0% error on the training data without doing anything almost. Or even some models, if you execute the learning algorithm in some way, it will give you the correct label for every example in the training data. That will give us 0 training error, right? And you might think that this is perfect. But we are not learning anything. So, a tree can classify training data perfectly. That's what I mentioned to you, the decision tree. But the main point here is that we want to test the model that we built on something that it didn't see before. So in new examples, it might give you incorrect answers. So imagine that we built the decision tree, okay? And we went through the learning algorithm as we discussed so far to the entire tree. And then I tested on new examples that were not used for training. Some of them might be incorrectly classified. Why? Why is that? Although I built the tree, and the tree learned everything from the training data, but when I gave it a new example, it might give me the incorrect answer. Yes?
The test data can be something that the model has never seen before.
Of course, but I'm asking why. Now this is given. We know that it didn't see before, okay? But why I would have error that is 0% on the training data, but it doesn't actually give me correct labels for the unseen data. Yes, Sulaiman?
Sorry. Because sometimes we can make a decision tree based on the wrong criteria.
Based on?
Wrong criteria.
But it was perfect for the training data, right?
And
it was perfect.
It was perfect for a specific scenario, and the other scenarios like that.
Okay, so you are very close now. Okay, so you are saying something that maybe the training data was not enough, right?
Yeah.
The training data is just a sample. We didn't see everything, as you said. We didn't see everything. The test examples are not seen in the training. The training is just subset of the entire possible instances, right? So doing well on that might not translate completely to doing well on unseen data. Okay? So we are not targeting training the error here, because we can easily reach 0% error. But what do we target? Testing on unseen data. Testing on unseen data. Do you remember what did we call that in the very first lecture? No, I told you that if there is something that you should come up with from this course, this is this concept. Generalization. Exactly. Generalization. Okay? Generalization means that when you train a model, it do well on not another model, another data, unseen data. Okay? Unseen data. That's the generalization. I gave you an I teach you during the course. I gave you many examples during the course, and then I want you to generalize on the exam, because you will see problems that you didn't see before in training. Okay? But you learned something from what you saw in the training. Okay? Fine. So our target is not the training error. Our target is the expected error or the expected loss. Okay? Our target is the expected loss, not the training error. Of course, we will try to relate them. Okay? There is some relation. Okay? But that needs more details. Okay? That we'll cover, inshallah, this lecture and the next one. Okay? So we care more about generalization. So this is the formalization now. We have a loss function. We have a sample from some unknown distribution. But our task is to compute the function, is to get the function, the best approximation, that has low expected error, not low training error. Okay? Yes?
So we don't want always like 0 and we want it to be somewhere around 10, 20, like we want it to be low.
No, I cannot tell you the percent. We will see how we can, what should we do? Okay? But it's not that simple. Okay? Okay, so we care more about generalization to new unseen examples, not the training error. Right. With that, we'll start the new session. So that was the end of session 1 that we started in the first lecture. Okay, so you went through introduction, went through decision trees and what do we mean by decision trees and how we can train them, and then how to formalize the learning problem as a function approximation. Now let's talk about the limitations. Okay? Right. The main point in this session is to tell you that machine learning is not magic. Just throw some data, you will get a model and you are done. That's not true, because machine learning will not always work. So I want you, with this session, to understand that machine learning has limitations. Okay? It might do well on this case, but it might not do well because of these reasons. Okay? So we have to keep that in mind. So what we will cover in this session are 4 things. Inductive bias, again, remember that we talked about it in the first couple of lectures, or maybe first lecture in particular. Why might machine learning fail? We will talk about 2 important concepts in machine learning called overfitting and underfitting, and then how we can test the model's generalizability. Yes? Raise your voice, please.
I'm just going to go back a little bit. Now,
Back. Do you want me to go back in the slides?
No.
Okay.
So let's say we have new data coming. And
Let's say we have,
we're using new data.
okay, unseen data. We are using unseen data.
So it will be wrongly classified.
It might be.
Why?
Yes.
So how can it be correctly classified?
Stay tuned. We will talk about that. Okay, we'll talk about not correcting, but we'll talk about how we can properly evaluate and make the model better. Okay. Fine. The first thing is inductive bias. Do you remember what we discussed when we talked about inductive bias? Do you remember this example? I showed you some examples in class A and some examples in class B, and I asked you to classify these, right? Some of you come up with bird versus not bird, some flying versus not flying, and I also told you about the background in focus or not, right? And we said that these are examples of what we call inductive bias. Okay? each one of us learn in different ways, okay? And these ways are affected by our assumptions or our hypotheses. These hypotheses are called inductive bias, okay? So inductive bias, we can think of it this way. Before I see the data, do I have some assumption about the relationship between the examples and the classes? Do I have some assumption about the data before I even see it? This is what we call inductive bias, okay? And each learning model or learning algorithm that we will study has its own inductive bias, has its own assumption before even we see the data, okay? طبعا, of course, some of the assumptions will be more probable than others, and we saw that in the previous example, right? The assumption that the background will determine class A versus class B is very improbable, right? None of us came up with that. But other assumptions like fly versus not fly, it has more probability. So it depends on the learning algorithm. So approaches differ primarily in the sort of inductive bias that they exhibit or have. Okay? So again, inductive bias simply, before I see the data, what are the assumptions that I am making about the mapping between the data or the examples or the features and the classes? Okay? Fine. Let's say that we want to study the inductive bias in decision tree, and I will give you a small modification to the algorithm that we saw before. Okay, so the algorithm that we saw before will stop at any path in two conditions, right? Do you remember these two conditions? Yes, Mahmoud?
Wasn't it the person that showed that there's the answer?
No, when we build the tree, while we are building the tree, okay, we in one path we might stop, right? We check two conditions before we stop. Okay, what were these two conditions? Yes, remind me of your name. Azam.
You run out of questions.
When we run out of features, okay, in that path, so we asked all questions already.
Or that the answers we get are all true or all false.
Yes, or if the data distribution at that point is all of the same label, so we should predict right away. Okay, we'll add a third one here, so that we will grow the decision tree, but with max depth. What do we mean by max depth? With the threshold of the number of features that we look at in any path. So let's say that the max depth is 3. So we cannot, in any path, if we split it on 3 features, خلاص, done, we will stop at that path, and we have to predict right away. Of course, we will predict based on the scoring criteria that we are using, the majority voting in the case that we studied. Okay? So that will prevent the tree from going very deep. Okay? So it will shorten the tree. So for example here, this is a funny problem, is a person fit or not? Okay, so we'll assume here that the tree will have a depth of 2 only. So we'll have to ask maximum 2 questions at any branch. Okay, so if the age is less than 30, then if the person is eating a lot of pizzas, then is unfit, otherwise it's fit, and so on. Okay, so this is an example of a tree that has a depth of not 3, 2. It depends on the number of questions. Okay. We are not counting the leaves here. Okay, the leaves are not questions, the leaves are predictions. Okay, so the number of questions here is is 2, and the maximum depth here is 2. Okay, so that's a third criteria that we can add to, and this is actually the one that is used in practice. Okay, so the learning algorithm that we started with is not the one that we should use. Actually, we should add this. Okay, for a reason that we will discuss later. Okay, but you understood now the modifications, right? Fine. With that, what is the inductive bias? If I told you that I want the tree that I will build has a maximum depth of 5. Okay, and let's say that we have 100 features. Okay, but the maximum depth will be 5. And every decision tree that I will build, even with other data, it will have maximum depth of 5. What is the inductive bias here? What is the assumption here? When I'm asking you about the inductive bias, think about what is the assumption that the model is having regarding how the predictions will be done. If I told you that I will have decision trees always of depth 5, okay? You understand first what do you mean by that, right? Now, what is the assumption behind that? If now I build a model that has a maximum, a decision tree that has a maximum depth of 5. Yes, that means that it has maximum 5 questions or 5 features, okay? But what is the assumption here? Assumption regarding the classification. Remember that we are doing classification here, right? Omar?
We have bias towards the first top 5 features.
Okay, what's the consequence of that? Yes, I will look at 5 features maximum. That's the meaning of that. But what is the consequence of that? What am I assuming now? Okay, what is my target here? When I build a decision tree, what is the target? What is the goal? Making predictions, right? Making any predictions or making correct predictions? Making correct predictions, of course, right? So I hope when I build the tree to make correct predictions. So when you tell me, when I'm telling you that the depth of the tree will be 5, I'm making an assumption here. What is that assumption? Yes?
5 questions will lead to the correct.
Yes, that 5 questions will be enough to make correct classification, correct predictions. That's the inductive bias. Did I get that from the data? Do I have to look at any training data? That's an assumption even before the data arrives, before I see the data. That's the assumption about the learning algorithm itself. It doesn't depend on the data. Okay? So the inductive bias in this case is that D, or whatever the depth is, D questions will be enough to make correct predictions, regardless of how large the data is. Maybe I have thousands of features, maybe I have millions of examples. 5 or D, whatever the D is, will be enough for the classification. Yes?
You will be at the end one answer. It will be what is the depth? It will be one answer.
Of course, because I will reach at the end, when I traverse the tree, I will reach one leaf.
That means one value.
Yes, of course, one value, one label. Okay. Any other questions? Is the point of an inductive bias clear? Is that a limitation? Yeah, the inductive bias in general, is that a limitation?
Yes.
Of course it's a limitation, right? Of course it's a limitation. Every learning algorithm will have some bias like that. Okay? So it has some limitations. And these biases might affect the performance, of course. Right? Is every problem solvable by asking 5 questions or 10 questions? No. But it's just an assumption. Okay? The second point that we want to talk about today is that not everything is learnable. What do we mean by that? Imagine that we have a machine learning model that we trained already, and we want to know when can this model fail. Fail means, of course, making incorrect predictions. One very simple reason for failure is that we have very small training data. So the model didn't have enough data to learn from. Okay? يعني in the example of predicting the age from pictures or images, if I give the model just one image, one example, do you think it can generalize to others? Of course not, right? So that's a source of error, source of problem. That's the simplest problem that can make the model fail. Fail means, of course, making incorrect predictions. Okay? What else? Noisy training data. So we might have a good number of training data, but it's noisy. What do you mean by noisy? It might have problems in the features, might have noise in the features, or might have noise in the labels. Noise in the feature values themselves might be noisy, might be incorrect. Okay? These features are observed somehow. The feature values that we see in the training example are observed somehow, right? We got them from some sources. These sources are not perfect. You might, instead of getting a value of 24, you might get it 4, might get it 2, might get it 20 instead of 24. Okay? So there might be some noise in the features. And there might also be some noise in the labels. And instead of labeling that example to be positive, it might be labeled as negative incorrectly. Okay? Of course, if you give the training data like that, we cannot expect that the model will correct it easily. Okay? Some models might be affected, of course, by some problems in the labels. Yes?
And this might also mean that we can have like maybe duplicate collection. Like maybe we can give it the same training data and we will have the same.
That's the next point. Okay, or the point after that. We'll get back to that. Okay? Yes?
Can you give an example for noise in the future?
Okay, noise here means that there might be error in the values itself. Okay, so instead of I'm 47 now, or about to be 47. Okay, maybe my age will be written as 40 instead of 47, or 37, or 7, just by mistake. Okay, that's an error in what? In feature value or in a label? It depends on the problem, right? If the problem is age prediction, then in the label, because the label that I want to learn is the age, okay? Or it might be in another classification problem, and age is just a feature, and then it will be just a feature value that has the noise. Okay? Is that clear? Right. Features also might not be useful or insufficient. And we saw that in the temperature in the example in the playing tennis example was not used, right? So might not be useful. Maybe, let me give you another example. Maybe we in that example I might give you the just as a feature might give you the color of the eye of the player. Would that be useful in deciding whether to play tennis today or not? Or the color of the hair or whatever? Okay, so some features, and it might be by coincidence that some features that are in reality unimportant might correlate with the labels. So that can be a source of error. Okay? Or the features are insufficient. For example, I want to predict your performance in this course, but I only have your grades from the previous semester, only. Will that be sufficient to learn your performance in this course? Might not be sufficient, right? So the features here, whenever you will learn from that features, will not give you good indication of your performance in this course, okay? So these are limitations. Remember that the title of the session is limitations. So these are limitations. This will limit the quality of the model that we will learn using machine learning algorithms. Yes?
What's the relation between not everything is learnable, so noise and very small training features?
Because you might get, now not everything is learnable means that you will not learn it perfectly, or you will not learn it in a good way. Okay? So here, of course, but our target is to minimize the error, right? Our target is to make always correct decisions as much as we can. Okay? So what can limit that? What can prevent that? What can cause many errors in our predictions? Okay? Is that clear? So what else? Some examples might not have single correct answer, and I think this is related to your point. What do you mean by that? we assume that we will have in the training data, we will have example and a label, right? Example and a label, right? There's an assumption here that this example has just one label, one possible label. But in reality, one example might have different labels. That's also related to what you mentioned. And let me give you a clear example here. When we search in Google, okay, let's say that we wrote Qatar University. And in the first result that we get, it was the homepage of Qatar University. Okay, I might be happy with that because my intention was actually to reach the homepage of the Qatar University. But someone else might not think that this is relevant. My intention is not to reach the homepage. My intention is maybe the ranking of Qatar University or research in Qatar University or something like that. Okay, so same example, which is the query that we wrote and the page, that's same example, same features, but in reality it might have different labels. I might think that it is positive, someone else might think that it is negative. Okay, yes?
The model, when we put different way, what the model will us
It will be confused, of course. It will not give. This is a source of noise. That's a source of noise.
Okay. I have also another point.
Yes.
About
About the what?
About the point for
The failure. Okay.
For different fields like medical, we can if you want to get let's say someone have a disease,
Mm-hmm.
give him a medicine.
Yes.
We can do that because
We have to know many things in the history of the patient before we recommend the medication.
also some like I have some diseases have the same
Symptoms.
yes.
Yes. That's perfect example. Which one of these is that source of error? Can you think?
About some examples. For example,
Tell me which one of these four is the type of error that you just mentioned. So he's saying that sometimes, for the example that he's saying that I want to build a machine learning machine learning system that will recommend medication to a patient, okay, based on some symptoms. Okay? Of course, as he said, and I think we all agree, some symptoms are very common between different diseases, right? So I might give incorrect medication. So that's a limitation. There is a source of noise here. Which of these four is that type? Yes, the last one. What's your name? No, not. Yes.
The features are insufficient.
Yes, the features are not sufficient. Features are not sufficient. Okay, these kind of symptoms are not sufficient. Maybe I need to know some history about the patient. Okay, maybe he didn't give all the symptoms. Okay, so these are all limitations. Yes.
I think some examples might not have the single correct answer because there's.
That's the last one, right? That's the example that I.
I mean,
I think most of them are
That's in the assumption here. You are assuming that the patient might have both diseases or not just one, right? It can happen, of course. And if that's the case, then it is the number 4. Okay. Yes. Any questions? Okay. Type. The last one is what we actually mentioned, I think, 10 or 15 minutes ago. Is that sometimes there is a mismatch between the inductive bias of the learner, of the learning algorithm, and the concept that we want to learn. Referring to the example of the birds, okay? The algorithm might learn that the basic feature that we should look at is the background. Of course, it shouldn't, right? Okay, so that's a mismatch between what we actually want to learn and the inductive bias. Okay, so sometimes the assumption behind the learning model is very far from what we actually want to learn from the data. Okay, so all of these are sources of error. Of course, potential sources of error. Okay, in one case, in one example, in one application, you might have one of them, or you might have more than one. Okay, and that, of course, will limit the quality of the model that we will get. Okay, you have to keep that in mind. Type. The last thing that we want to cover today, I think, based on the time, is what we call overfitting versus underfitting. So what is that? We want to evaluate the learned hypothesis. Remember that we have a set of hypotheses, and we want to get the best of them, right? So in decision trees, the learned hypothesis is the decision tree that we trained. So we want to evaluate it. Okay, and we said that it can fit the training data perfectly. We might get zero training error, but of course, that doesn't mean that we are done. Okay, as we discussed in the beginning of the lecture, having perfect predictions on the training data is not enough, is not even the goal for us. And we cannot, of course, guarantee that we have found a good hypothesis, because it might not generalize. When we test it on unseen data, it might not give us correct predictions. Okay? So the performance in this case, the performance on training data is not representative, is not good enough. I mean, the estimation that we got of the performance is good enough, is not good enough. So training error is not sufficient. This is what we mentioned, and we care more about generalization. Now, there are two extremes. Okay? Overfitting means that the model will learn every single detail in the data. So we'll learn everything. Even if there is noise in the data, and that's of course possible, it will learn this noise. Okay? So this is like, it will classify the training data perfectly, because it will learn every single detail in the training data. Okay? This is called overfitting. Because we are not fitting the data, we are fitting data plus the noise that is in the data. And that we should not do. So rather than what we are supposed to learn, we will learn many other things. Okay? Right. Let's think about overfitting in decision tree. When we grow the tree without any possible depth, that means that all the leaves probably at the end will have in the subset that we have in the end just one example. That means that there is, for every example in the training data, we have one complete path. We are kind of memorizing every single example in the training data. That's overfitting. That's overfitting. Okay? We are not generalizing. We are learning for each example, we are learning a new path. Almost, kind of that. Okay? Type. Overfitting in the student, remember the example that we started with in the first lecture when we talked about course learning in a course? Okay? What will be overfitting in this case? When we learn every single detail, okay? What will be overfitting?
Generalization?
No, that's the opposite, right? What is the opposite of generalization? Type. Yani, overfitting means what? Means that we are doing perfect on the training data because we learned every details, even details that we should not learn. Okay? And that, of course, will cause errors when we test on unseen data. Okay? Type. In the student course understanding, okay, what is the overfitting? What does the overfitting mean here? Learning in a course is very similar to machine learning in general. Okay? If I will test you on the exam, Okay? In the case of overfitting, you are doing very well during the course, but when you are testing in the exam, you will easily fail. Why? Yes?
You are having zero error inside the training.
Yes, zero error in the training here means what? Tell me, in a course, when we learn in a course. Muhammad, right? Yes?
Like, for example, you learn the course syllabus, the course overview, and everything.
Yeah, you memorize all of these things. Okay? You memorize. And in our example, in course, you memorize the examples that you saw. You memorize that this problem will be solved this way. And that problem will be solved this way, even with the numbers. Okay? You memorize the outcomes. Now, if you do that, then of course in the exam, when you get different problems, you will completely fail. Because you just memorized, you didn't learn. Okay, you didn't learn. So that's the problem. We'll have to stop here with the last question. Yes?
It means that overfitting, that we are good at something, and when we go to the serious matter, we cannot do it. Like
You thought that you are good
Yeah.
by memorizing. Okay?
Yeah.
But I would better say it, we learned even the noise. Okay? We learned much more than what we should. Okay? That's why we didn't generalize well. Okay? We'll continue talking about that inshallah next time. Assalamu alaikum.